We're going to take the same question and look at it a different way. So we had that a person can reduce the pressure in their lungs to negative 53 millimeters of mercury gauge pressure. We're going to calculate the maximum height of straw the person could use to drink a glass of water. Now, in the last video, what we did was we took this 53 millimeters of mercury and turned it into a pressure in kilopascals. So taking a look at the picture here, I have a glass filled with mercury with a tube inserted into it, and at the end of the tube, at the top of the tube, we have a vacuum chamber. At the vacuum chamber, we reduced the pressure down to, we reduced the pressure by 7.07 kilopascals, and because we have atmospheric pressure everywhere else, that change in pressure forces the mercury to go up the tube. How far up the tube? 53 millimeters. Now, if we were to take the same setup with the same atmospheric pressure, the same difference in pressure, but this time change the mercury to water, then what would happen is, because the water is less dense than mercury, the water is not going to be weighing down so much. So there's not going to be as much, force pushing back against the atmosphere. And the water's going to rise higher. If you watched the last video, you know how high it's going to go. However, right now in this video, we don't know, so we're going to find that out. So as I said here, everything is exactly the same in these two experiments, except here we have mercury, here we have water. And the main difference between mercury and water is their density. We know from the last video that the density of water is 1,000 kilograms per cubic meter, and the density of mercury is, well, we weren't told that in the last video, but I looked it up on Google and it said 13.56 grams per cubic meter, which is the same as 13,560 kilograms per cubic meter. Whoops, that was a centimeter. So we know that the pressure in here is the same. The pressure of water equals the pressure of mercury. We also know that pressure equals rho g h. So what we can do is we can equate these two so that we have pressure of water, density of water times gravity times the height of water, the height of the water column, is equal to the density of mercury times gravity times the height of the mercury column, which here was 53 millimeters. We can see that there's a gravity on both sides of the equation, so I'm going to cancel them out. We want to end up with water, so I can rearrange all of this to get H, that's the height of water, equals the density of mercury times the height of mercury divided by the density of water. Density of mercury here, 13,560 kilograms per cubic meter. The height of mercury is 53 millimeters. Milli just means times 10 to the negative 3, so I'll just pop that in, times 10 to the negative 3 meters. Now, I'm not going to put in that Hg there because that's just a signifier to tell us, hey, this is mercury. It's not an actual unit. And then going to divide all of that by density of water, which is 1,000. Now, you might be thinking, hey, where did that minus go? I didn't bring it in here. Well, the reason I didn't bring it in is because of the way I've set up my pictures. So in this picture, what we're doing here is we're reducing the lung pressure to negative 53 millimeters of mercury. But as we do that, that means that the mercury itself will rise up by 53 millimeters. And that's what we're wanting. We're wanting the height of the straw. So that's why I've removed the negative. Let's take a look at the units. Kilograms per cubic meter, kilograms per cubic meter. One's on the top, one's on the bottom. They cancel out. We're just left with meters. So if we take our calculator, 13,560 times 53 times 10 to the negative 3 divided by 1,000, we get 0.719 meters of water. I'm not going to put it in that of water part. So again, just like last time, we have 0.71, why am I redoing that? 71.9 centimeters. In the last example, we got 72.1 centimeters, so it's a little bit off, but that's just because of rounding errors.